Welcome back, and the small signal analysis. Now, what about the frequency response? We already have a hint regarding the frequency response. We have already seen that this CDB is going to play a role in the frequency response. So, how do we calculate, in a comprehensive manner, how do we do the more comprehensive frequency response analysis? We are just going to discuss some shortcut which is going to be very handy in doing frequency response analysis for more complicated circuits. So, all of you definitely might have come across the frequency response of simple circuits like common source amplifiers, and for many of you it may be redundant, but definitely as we have said, we have to cater to people even working in digital domain, and for them it is important that we have the basics being covered before going to the system level design. So, let me talk about common source amplifier frequency response. So, for that, once again all we need to do is add the high frequency capacitances to the small signal model. So, I will redraw whatever I had earlier, the same model, but with added small signal capacitances. So, what are the capacitances? Let me mark the terminals G, D and S, right, and assuming that body is grounded. So, you will have CGS, CGD, CDB and CSB. Now, B, we are assuming that B is grounded, S is also grounded. So, CSB is not considered, only CDB. Now, here we have the overall circuit. We can find out the first cruder or more complicated way of solving this question is to find out the differential equation solution, write down the differential equation in time domain at this node and this node, that becomes a coupled differential equation. We can solve those to find the solution of the time domain signal. But in general it is much more convenient to do frequency domain analysis, where we replace each of these capacitances with their complex impedance, which is going to be 1 upon SCGD, where S denotes 1 upon iota omega. So, in general in network theory, if you are having any capacitance or inductances, you can replace them by their corresponding complex impedances denoted by 1 upon SCGD in case of capacitance, and then the rest of the analysis is just like KCL or KVL analysis, right. So, here we can solve for these two node voltages, unknown node voltages, right. So, here if I add another complication, suppose if I put another source resistance R signal, in general a source will have some non-zero resistance, non-zero impedance, suppose it is R signal. So, in that case even the Vg is not known to me. If I do not have R signal, then Vg is equal to V signal or Vgs, but in this case the Vg is not equal to V in if I have a R signal. So, Vg becomes an unknown. Likewise, Vd is another unknown. So, my intention is to find out Vd upon V in. So, I have two unknown voltages Vd and Vg. I can proceed with common analysis. I can write down the KCL at this equation, this node and the second node. I can solve those in terms of this complex impedances, and I can get a overall transfer function. For example, at this node if I write down the expression for KCL, Vg times the impedance of this capacitor SCGS plus Vg minus V in upon R signal plus Vg minus Vd into SCGD equal to 0. This is the overall KCL, currents going out of this node Vg into these 3 branches summed equal to 0. Likewise, I can write down the equation at the drain node. So, I can write down Vd upon Ro plus Vd upon Rd plus Vd upon the impedance of this capacitor, which is 1 upon SCdB. So, we get Vd times SCdB plus Gm VGS, which is once again Vg minus 0, and then the last component, which is Vd minus Vg upon 1 upon SCGD. So, SCGD, this is the second equation, and here we have two unknowns Vg and Vd, two equations. We can solve them and find out the exact expression for Vd as a function of V in. So, we expect it is going to be some polynomial in S, maybe A naught plus A1 S plus A2 S square, second order, because you have two capacitances. Likewise, B naught plus B1 S plus B2 S square, something of this sort. This is a generic expression. I can further factor it into a more friendly expression, 1 plus S upon, of course there is going to be some constant term. So, there can be some constant term also. So, we can factor it into the constituent linear terms, 1 upon S plus P1, 1 upon S plus P2, 1 plus S upon Z1, 1 plus S upon Z2. So, this is the general way, most common way of finding out overall voltage gain, so small signal gains in terms of the frequency dependent parameters, where P1, Z1, they are called poles and zeros, which are dependent upon the RC time constant seen in the circuit, right. So, in general this P1 and C1, they will depend upon 1 upon R equivalent, C equivalent, the RC time constants in the circuit. So, this method is of course a lot more cumbersome. Whenever we are trying to do this direct analysis, it can be very cumbersome, especially if you go for more and more complicated circuits. We are having more and more nodes with more unknown voltages. It will become more and more number of equations, and we cannot do hand calculation based on that. A circuit simulator can do it. It is running on a powerful computer. It can run many different solutions and find out the overall solution, exact solution and exact frequency response. But for hand calculation, for doing quick analysis, we use some tricks, we use some approximations which can give us approximately good results, fairly reasonably correct results, so that we can get started with the design. So, rather than going through this more complicated step, we go for an approximation. So, one of the key steps involved in that approximation, and most of you might be aware of that, is dealing with the Miller effect. So, all we need to do is need to get rid of the capacitances connecting two different nodes and reduce them to capacitances connected between those nodes and AC ground. So, here the CGS is between the gate and AC ground, CDB is between the drain and AC ground, but CGD is appearing between two nodes of the circuit, and that is leading to coupling between these two equations. If CGD were absent, then the equation of the first node is solvable independently, and based on that Vg, I can solve once again the Vg, Gm Vgs and get the Vd independently. So, that decouples the two nodes. I can proceed step by step and find out all the signal without doing this coupled solutions. So, that is the main motivation behind using Miller theorem to decouple or disconnect the small signal parasitic capacitances connecting two circuit nodes and represent them by equivalent capacitances connected between those particular nodes and AC ground. So, what I would like to do is I would like to get rid of this CGD and represent this as an equivalent capacitance between this node and AC ground, and likewise between the other node and AC ground. This is what we would like to do, and Miller effects comes handy. That is what we are going to use for doing this simplification. So, without going into the proof of Miller effect, which can be done in 2 lines, but I am just avoiding that. Miller effect says that if you are having two nodes in the circuit, suppose you are having some connections over here, some blocks. So, I am just drawing two nodes, node A and node B, another two nodes, these are also connected to some other branches. I am not drawing node B, and you have ZAB connected over here. If I am talking about the small signal, you are having some relationship between the voltages at A and B. The small signal voltage gain at B as compared to A is suppose K. So, VB is equal to K times VA. Let me make it more clear. So, the small signal at B is K times V A. So, there is a voltage gain from the node A to node B, and under those conditions we can decompose this Z A B into an equivalent Z A connected between the node A and ground, and likewise equivalent Z B connected between the node B and ground. And the way we prove the values, we derive the values is just by equating the KCL. The KCL at node A should remain same as the KCL in this case, and it can be shown that the Z A is going to be equal to Z A B upon 1 minus A. Likewise, Z B is going to be Z A B upon 1 minus 1 upon A. So, if we apply this, sorry, K, so I have used the term K, so it is really K, that is the voltage gain from A to B. So, if I apply the same concept in this particular circuit that we have just arrived at, we can take an approximation. We can say that the low frequency gain from gate to drain, mind it, there is a low frequency gain, ignoring the effect of capacitances, the low frequency gain between the gate and the drain, we know it is going to be equal to GM RO parallel RD, approximately equal to GM RD. That is what we have done. We just did it in the last slide. So, the low frequency gain is just GM times RD minus sign, and therefore, the equivalent capacitance, if I look at their impedance, that is 1 upon SC. So, by this analogy, the equivalent capacitance becomes multiplied by C. If I have to find out CG, that gets multiplied by CGD 1 minus A, that is minus times GMRD, and likewise this is the CG dash which I am putting here. So, I am calling this at CG dash, which is the blue capacitor, equivalent capacitor obtained by splitting this CGD into a capacitor between gate and AC ground, that is CG dash, and that CG dash is just going to be CGD times 1 plus GMRD. And likewise, if I call this the other blue capacitor CD dash, which is obtained by decomposing CGD dash into an equivalent capacitor between drain and AC ground, then this becomes CD dash is equal to CGD times 1 minus 1 upon A. So, basically 1 upon GMRD. If I assume that GMRD is much greater than 1, then it is approximately equal to CGD only. So, basically what I can do is I can simplify this circuit. Now, my new simplified signal, small signal, is having CGS, it is having CG dash, which I obtain by breaking the CGD. I am having GM VGS, likewise I am having the RO and RD, and on this side I have CD dash, which I have just arrived at by breaking the CGD once again, and I also have CDB. Now, these two capacitances CGS and CGD, CG dash can be combined together, likewise the other capacitance can be combined together into a single capacitance, because they are appearing between this node and AC ground, and I can arrive at a resulting simplified model for my frequency response. So, I can call it CG, which is equal to CGS plus CG dash, this is RO parallel RD, and on the other side I have CD, which is once again CD, which is once again CD dash plus CDB. So, this is a much simplified model. I have decoupled nodes. So, now I have decoupled my VG and I have decoupled my Vd. And then the equation for Vg and Vd becomes very simple. I can just express Vg as V in times the impedance of this capacitance, that is 1 upon SCG upon R signal plus 1 upon SCG. That is just voltage division. This is the impedance of the capacitor, impedance of the resistor, R signal, and this is the Vg as a function of V in. We have simplified further, V in upon 1 plus R signal times SCG. So, here we see that we are getting a kind of low frequency pole of the order V in times 1 upon 1 plus S upon P1, right. So, where P1 can be written as 1 upon CG R signal, which is 1 upon C equivalent 1 upon times 1 upon R equivalent. So, if I go towards lower frequency, the CG is almost open circuited because 1 upon omega CG is very large. In that case, there is hardly any voltage division, entire V signal appears at Vg. That is what this equation is telling me, S tending to 0, Vg equal to V in. Whereas, if we go for higher and higher frequency, the impedance of this parasitic capacitance Cg reduces, and as a result the Vg is going to fall, and that is also given over here. The S increases. As a result, you can, when S becomes much larger than P, you are having a gain decreasing with S, that is the magnitude of the gain is decreasing with omega. As a result, you get a fall in the overall gain after you hit omega equal to P. So, and what is the slope? If I plot it in the log domain, if once I am having omega much greater than P1, then the transfer function Vg upon V in is approximated as V in divided by S upon P1, because we can ignore this 1 with respect to S upon P1. And then this means that once I am at omega much greater than P1, my magnitude of this gain, which is mod AV V in upon omega times P1, is going to reduce proportional to omega. So, if I go for 10x increase in omega, my gain is going to go down by 10x. In terms of dB, I can say, if I in this region, if I increase omega by 10x, if I am going from omega 1 to 10 omega 1, my gain will drop by factor of 10. In dB it is 20. So, I can say this will be a drop of 20 dB, and therefore, I get a 20 dB per decade drop in the mod AV. So, on the x axis we have omega, y axis mod AV. So, if I just consider this transfer function, it says that after you hit omega equal to P1, you are going to get a 20 dB per decade drop. Likewise, if I go for the output pole, once again I can, once I have the expression for V in, I can find out the expression for Vd, which is just Gm Vgs with a minus sign multiplied by the total Z that is seen over here. So, earlier we had only Gm Vgs times Ro parallel Rd, but now we have Gm Vgs times Ro parallel Rd parallel the impedance of this capacitor, which is 1 upon SCD. So, if I ignore Ro and I say that this is just approximately equal to Rd, then basically once again I have an expression which is Rd parallel 1 upon SCD, which is something like Gm Vgs Rd upon 1 plus SCD times Rd. So, once again, if I look at the first term over here, the numerator tells me the voltage gain is minus Gm Rd provided your S is very small. So, for very small omega, once again the term over here can be ignored with respect to 1, whereas in that case my overall gain is just minus Gm times Rd. But if I am going for larger and larger omega, once again this starts dominating, and once again you have the 1 upon S relationship coming. So, once again I can write this as minus Gm Vgs Rd upon 1 plus S upon P2, where P2 is the pole given by 1 upon CD times RD. So, this is once again I can combine this VGS expression that we obtained earlier. So, VGS as a function of V in we have already obtained. So, if I combine this equation 1 and equation 2, I can write down 1 plus 2 will give me Vg or Vd upon V in that we are interested in. So, first equation gave me Vg as a function of V in, second equation gave me Vd as a function of Vg. Combining this, I can just eliminate this Vg by putting Vg as a function of V in, and therefore, I get minus Gm Rd into 1 upon 1 plus S upon P1 times 1 upon 1 plus S upon P2. So, what we say is that in this transfer function, the Gm Rd terms is a low frequency term which will come when you ignore the effect of this high frequency parasitic capacitances. But once you include the effect of this parasitic capacitances, then you have these two frequency dependent terms coming into picture, which say that at higher frequency the gain is going to drop. And from this curve, from this expression, we can find out what is going to be the shape of this transfer characteristics mod AV with respect to omega. So, in general, if we carefully see what we have done in doing this simplification, we can observe a circuit and all we have to do is find out the low frequency gain. So, first term is the low frequency gain, and then find out what are the poles, what are the high frequency poles or the RC time constants associated with different nodes. So, these are the poles, and corresponding to that we are having the RC time constants associated with the two circuit nodes. So, at these two node voltages in the circuit, we have found out the RC time constants corresponding to the equivalent R and equivalent C. So, this is the step we are going to repeat for analysis or frequency analysis for more complicated circuits. Find out the low frequency gain and then find out the RC time constant at different circuit nodes. That is, find out the small signal equivalent resistance, call it 1 upon R2 equivalent, and find out the small signal equivalent capacitance C2 equivalent. What is R2 equivalent? That is the small signal resistance between that particular node and AC ground. So, at this drain terminal, if you see what is the small signal resistance between drain and AC ground, that is just RO parallel RD. Likewise, what is the C2 equivalent? That is the small signal resistance seen between the drain and the AC ground, that is just CD. That gives me the R equivalent C equivalent corresponding to the pole arising at the drain terminal. Same thing applies at the gate. So, at the gate terminal, if I see the small signal equivalent capacitance between this gate terminal and AC ground is Cg, and small signal resistance at this node between this node and AC ground, this is R signal, because V signal, once we have taken out R signal out of it, this becomes an ideal source, it does not have any resistance. So, this represents the internal resistance of the source. So, the equivalent small signal resistance between this point and AC ground is just R signal, the equivalent small signal capacitance between this node and AC ground is R signal Cg, and therefore, 1 upon Cg times R signal gives us the pole, the P1. And once we have this low frequency gain minus Gm Rd and we have these two poles, we have the frequency dependent transfer function of the amplifier ready. From there we can do more detailed analysis, we can find out the transfer curve for the magnitude and phase response of this circuits. Alright, so we are once we have this AC analysis done, the last so we have done DC analysis, we have done the small signal analysis, and finally we have done the frequency response. We will go into a little bit more detail of the frequency response, but just to complete the story, we are also going to look into very quickly the noise analysis that we have just discussed and how to link it with the circuit analysis. So, for doing the noise analysis, once again we are going to look into the small signal model and trying to see how to incorporate the noise signal at the MOSFET device. So, if I directly draw the circuit, we have RD and the MOSFET which is going to have its own noise. I can represent the noise source of the MOSFET as, of the RD as the equivalent current source, that is what we have seen. So, that is 4 kT upon R. This is the IN square F, that is the mean square noise spectral density of the RD. Likewise, I know I have a channel current noise for the MOSFET, I can call it IN square channel of the MOSFET, which is equal to 4 kT gamma GM, and I also have the 1 upon F noise of the MOSFET coming in series with the gate, which is we know K upon F W L C O X. Now, if I want to find out only the effect of these noise sources, I can set the input source to 0. I can set the input source to 0. I do not apply any external signal. I just want to find out, because of these noise sources within the resistor and within the MOSFET, what is going to be my output noise voltage VON square, that is the mean square output noise voltage. So, I can directly do the analysis here as well without going to the small signal model, but it will be more convenient, more clear if I go to the small signal model. So, I am drawing the Vn square G at the gate, that is corresponding to the 1 upon F noise. I am drawing the In square channel, which is 4 kT gamma GM. We are also having the RD, which is going to give you another noise source, right. So, this is 4 kT bar R, this is the gate terminal, source is grounded, and we want to find out what is the VON square. Remember, these are noise square, current square. So, we have basically first of all two current sources over here, 4 kT by R, you have the channel current noise 4 kT gamma GM, and we also have the transconductance term, which is going to convert this Vn square G into another channel current, which is going to come because of the GM term, GM square Vng square. So, remember, we have to deal with GM square because this is Vng square multiplied by GM square, it will give you the effective noise current in the channel. So, based on this, it is easy to see, means we have to just look at the square terms, we do not have to worry about the polarity of each of these current sources. So, this is the current which is coming between the drain and the AC ground. Remember, this is VDD. So, from the point of view of small signal, it is AC ground. So, we can ground it. So, this 4 kT upon R is coming between the drain and the source. This IN square channel 4 kT gamma GM again coming between drain and the AC ground. So, IN square channel coming between drain and the AC ground. RD as usual between drain and AC ground, because this is drain and AC ground, and likewise the GM square term, which is going to convert this noise gate voltage Vng square. So, Vng square multiplied by GM square gives you GM square Vng square as a drain to source current, so the current noise current. So, these are 3 currents that are coming in parallel, and all I need to do is sum them up and multiply with RD square, because these are current square and we need to add up the mean square values of this current. So, basically what I have to do is output VON square is going to be equal to 4 kT upon R plus 4 kT gamma GM plus GM square K upon F W L C O X times RD square, that is all. And now, what we have seen is it is convenient to represent the noise as an input referred noise. So, this is the output noise voltage VON square that we are calculating. How to refer it to the input? What is the equivalent input noise at the gate which captures this entire output noise? So, input referred noise can be written as VON square divided by A square or AV square, where AV is the magnitude of the gain. What is the magnitude of the gain? At low frequency, if I assume the low frequency behavior, AV is GM RD, therefore AV square is GM RD square, right. So, then I divide the whole thing by GM RD square, and therefore, RD square gets cancelled and VIN square will be 4 kT upon GM times RD plus GM square times RD times 4 kT gamma upon GM plus K upon FWLCOX, that is the input referred noise V in square. And we see some interesting results. We see that the input referred noise is inversely proportional to RD. We would expect that if RD is large, its 4 kT R noise voltage will be large, but here we say that input referred noise is lowered if we increase RD. Why? Once again the same phenomena, because larger RD also amplifies the input signal going to the output. So, although it is producing some noise, but it is also amplifying the signal, so that as compared to the input referred noise over here, the signal strength will be increased. So, if I talk about the signal strength at the output, that will be amplified because of RD. Therefore, the noise or the signal to noise ratio that is getting improved if you are having larger RD. Likewise, we see that there is a strong dependence on GM. So, if you are increasing GM, the first two terms definitely tell us larger GM means smaller input referred noise. So, having a larger GM for the input device, which can be obtained either by increasing ID or it can be obtained by increasing W by L. So, W by L or larger ID will help me in reducing the first two terms. Likewise, the second term larger W as well as L will help me reducing the 1 upon F term, which is very significant for low frequency operations. So, we see that you have to reduce the 1 upon F noise, that is going to be taken care by choosing larger W and L. But once again remember, if you are choosing larger W and L, what is the issue? We know that larger W and L means lot of parasitic capacitances. All the capacitances that we have discussed will scale up, that will make your circuit smaller, slower, parasitic poles will become lower, and therefore, your frequency response, the lower cutoff, the higher cutoff frequency will be lowered, bandwidth of the circuit will be limited. So, if you are trying to reduce the input referred noise, it can ultimately trade off with your area as well as the bandwidth or the speed of the circuit. Likewise, if you are relying on GM to increase your signal or reduce your noise, once again larger GM means either larger W by L or larger ID. So, either it can increase your power consumption because of larger ID, or once again if you are choosing larger W by L, it can increase your capacitances and hence the circuit can become slower. So, there are a lot of pros and cons. The moment you try to fix one parameter, try to adjust the noise, it trades off with your gain, it can trade off with your power consumption, it can trade off with your linearity that we have not discussed in so much detail. So, this is the step we are going to follow for rest of the circuits, and just to complete this discussion, if I plot this transfer characteristics, if I try to see, there are two terms, one is the 1 upon F dependent term and other two terms are constant terms. So, the frequency at which this 1 upon F term becomes equal to this constant term is generally referred to as 1 upon F corner frequency of the circuit. So, if this is your Vn square and at this F, the contribution of this 1 upon F term is becoming equal to the contribution of this constant term, that is called the 1 upon F corner frequency. Beyond this point, the 1 upon F noise is picking up, its contribution is increasing steeply. Above this point, above this frequency, the white noise term, the frequency independent term, that is more prominent. So, in case your signal is in this region, that is below 1 upon F, definitely it will get corrupted by very large noise in this region. So, we need to take care of that. So, corner frequency happens to be another very important concern while doing noise analysis in circuits. So, this is the analysis we are going to follow. This is the scheme overall, starting from DC analysis, DC biasing point, going to small signal low frequency analysis, frequency response, transfer characteristics, the magnitude and phase response, and finally the noise analysis. So, these are the 4 basic tools we are going to repeatedly use in designing more complicated building blocks for our analog front end. So, we will start our discussion on the front end amplifier, start with the building blocks, the differential amplifier with active load. We will also look into current mirrors, and then finally develop the entire scheme with appropriate DC biasing, with optimization of noise, with optimization of bandwidth, and looking at the complete picture. And then we will use that front end amplifier with some other signal processing schemes to take care of some of the critical issues like this 1 upon f noise, especially in case we are dealing with very low frequency signals. So, that is going to be covered tomorrow, and hopefully we will be completing the analysis of a front end amplifier based on the material that we have prepared today. So, thanks a lot